Calc Chats number 7. Today we're going to talk about left and right Riemann sums. So far we've discovered that a definite integral is the area underneath any given curve. We've been able to use simple geometry to help us find these areas, but we're going to be faced with some scenarios where it's not always an easy geometry formula that we can use. So given this parabola, if I wanted to find the area underneath this curve from -1 to 1, kind of just looking at it, my first instinct would be to use a semicircle. But although this kind of has a circular shape, it's not a perfect semicircle. And so it wouldn't be the best approximation of the area underneath that curve. So today we're going to be using these things called Riemann sums. And Riemann sums are just another way to find the area underneath any given curve. But in order to use these Riemann sums, f of x has to be continuous, and it also has to be on a closed interval from a to b. We're going to use what's called the rectangular approximation method. And so basically it's just a special kind of Riemann sum where we use a bunch of tiny rectangles to best get the area underneath the curve. So remember, we all looked at our geometry formula sheets. Area of a given rectangle equals length times width. And that's really the only area formula that we need for these particular approximations. So we have LRAM, which is called the left rectangular approximation method. And what this means is I'm going to use a bunch of rectangles, but I'm going to start at the left-handed point on the function. So we could be given some kind of problem that looks like this. Find the area under the curve from the intervals 0 to 4 using LRAM and delta x equals 1. So this delta x, that's our width. So that tells us that we're going to be using, on the interval from 4 to 0, we're going to be using 4 separate rectangles. So if we look we go back up, we see that the interval from 0 to 1, that has a width of 1, 0 to 2, 2 to 3, and 3 to 4. So we're going to be using our basic tick marks on our coordinate plane to find these rectangles. Now this is kind of where it gets a little bit tricky. So we have our width, but we're going to need our length of our triangles. And the length of our triangles is going to be f of whatever x value we're looking at. So if I'm starting from the left and moving over, if I'm starting from this first point, 0, I'm looking at the point x equals 0. So in this function, we're looking at y equals the square root of x plus 2. So this is our function. So given x equals 0, we're going to say square root of 0 plus 2 is just 2. So my rectangle has a height of 2 and a width of 1. So that's kind of what my rectangle looks like. So we go over to 1, again starting at the left hand. I'm going to plug in 1 for x. So x equals 1. I get the square root of 1 plus 2. That's just going to be 3. So this time my rectangle has a height of 3, a length of 3 and a width of 1. If I look at x equals 2, that's my next stopping point, again from the left-hand side. I'm going to plug in 2, so I get the square root of 2 plus 2. And that is approximately 3.414. And so my third triangle, or my third rectangle, has a height of 3.414. And my last rectangle, I'm going to be going from x equals 3. So the square root of 3 plus 2, and that's about 3.732. So I have all my widths, they're all 1. I have all my heights. And now what I'm going to do in order to find the total area is I'm just going to sum all of those areas together. So my first area, or my first rectangle, had a length of 2, a width of 1. Second rectangle, length of 3, width of 1. Third rectangle, length of 3.414, width of 1. And my fourth one, I'm just going to add that one, had a length of 3.732 and a width of 1. So all I'm going to do is I'm going to add those all together, and I just punch this in my calculator to get 12.146. So this is my LRAM approximation of the area under the curve, y equals x squared plus 2. So RRAM is a similar method. We're going to be using the same type of rectangles, but instead of starting on the left side of our interval, we're going to be starting on the right side. So here I'm given y equals x minus 2 squared. And I want to find the area under the curve from 0 to 3 using RRAM and n equals 3. So n equals 3, that's the number of rectangles. So this doesn't tell me my delta x. This doesn't tell me my width. So I need to find delta x first. And how I do this is I take my endpoint, so 3 minus 0. So I want to take b minus a all over our n. So in this case, our n is 3. So here I get 3 over 3. So I get 1. So that is my delta x. That is my width of my triangle, or my rectangles. So if I go back up, I'm going to be using a width of 1. So again, I'm just using the tick marks that I have. That's super nice. So 0 to 1, 1 to 2, and 2 to 3. So in our first approximation, we went from the left. So if I was using LRAM, I would start from 0. But when I'm using RRAM, I'm going to start from the right side of my interval. So I'm going to start from 1. So I'm going to make a rectangle. And if I plug in 1 to my function, so at x equals 1, I get 1 minus 2 squared, and that is just 1. So this rectangle has a height or a length of 1 and a width of 1. If I'm looking at x equals 2, 2 minus 2 squared, that's 0. So this rectangle doesn't have a height, so it's just going to be a straight line. It's just going to be 0. And then my last right-hand side, so from x equals 3, 3 minus 2 squared, that's equal to 1. So this also has a length of 1 and a width of 1. So as we can see, this is probably not the best approximation method, because we go far above our curve, but then we even have one rectangle that's not even a rectangle, it's just a line. So this probably is not the best approximation, but let's find out anyway what it looks like. So I need to plug in my length and width. So my first rectangle had a length of 1, a width of 1. My second rectangle had a length of 0, a width of 1, and my third rectangle had a length of 1 and a width of 1. So this ends up being 2. So this is my approximation of the area under the curve, y equals x minus 2 squared, using the RRAM. And as you can see, not the best approximation. So really quickly, we're just going to go over using LRAM and RRAM from a table. So rather than having it on a graph, you could be giving a table of information. And so again, we're still going to have it split up into our separate little intervals. So as I see, this is the interval from 0 to 2. Then I have the interval from 2 to 5. interval from 5 to 7, and then the interval from 7 to 8. So again, my width is my delta x. My width is my change in x. So from 0 to 2, that width is 2. From 2 to 5, that width is 3. From 5 to 7, that width is 2. And from 7 to 8, that width is 1. So I'm just, from 0 to 2, I'm just going over 2 spaces. From 2 to 5, I'm going over 1, 2, 3. From 5 to 7, 2. And from 7 to 8, 1. So I'm just counting the difference between those two numbers. For LRAM, I'm going to use the same widths as I get up here. So I'm going to use my widths. But then my lengths are going to be the left-hand numbers on that interval. So if I look at my first interval from 0 to 2, my width is 2, and my length is the left-handed side, so 0. On the interval from 2 to 5, the left-handed side is 4. So my width is 3, length is 4. On the interval from 5 to 7, width is 2, length, left-hand side, 13. And from 7 to 8, width is 1, length is the left-hand side, 21. When I add these all up, I get that my LRAM is equal to 59. So I did my LRAM, and now I want to look at my RRAM. So RRAM is kind of the same idea. We're using the same widths that we get from our intervals, but the lengths are going to be the right-hand side of that interval. So if I'm looking at the interval from, let's say, 0 to 2, my width is 2, and my length is going to be the right-handed side, 4. Again, from 2 to 5, my width is 3. My length is going to be 13. From 5 to 7, width is 2. Length is 21. And from 7 to 8, width is 1. And length is 23. And when I add these all up, I should get 112. So we can kind of look and see that this is quite a drastic difference from the LRAM and the RRAM. And so in class, when we practice, we're going to look at which ones are going to be the best approximations for certain types of functions. So this is the end of the video. Make sure to come to class with any questions that you may have, and please like and subscribe.